Okay, so let's go ahead and get started. Hello, everyone, and greetings to all our customers joining us from around the world. I'm Lokesh Shara, the Senior Manager for Arista's Technical Services team, and it's a pleasure to welcome you all to our exciting webinar series graciously hosted by the Arista TAC team. So whether you are joining us for the first time or returning after a break, I'd like to briefly outline the purpose of these sessions. Our goal is to share the knowledge that we have cultivated in the Arista TAC world with our customers and focusing on the topics that are highly relevant and beneficial to everyone. We launched this initiative in 2022, and over the past 2 years, we have delved into various technical topics, including switch health checks, Layer 2, Layer 3, VXLAN, and EVPN debugging, both from the CLI and Cloud Vision perspective. We have also brought in different Arista product lines into the mix as well. And recording of all our previous sessions, including the presentation material and the Q&As that we covered, are available on our Arista community page if you'd like to review them. Coming to 2024, earlier this year in Q1, we did a deep dive into troubleshooting network latency and the traffic black holing problems. And in Q2, our focus is on a topic where we have received a lot of customer demand, and that is multicast. Today's session is our third session in our multicast series, overall sixth this year, where we'll do a deep dive into the debugging gaps in the multicast packet stream. For today's session, we have our senior technical lead and multicast expert, Upasna Dangi, who is back on popular demand. Upasna will be walking us through a few debug scenarios related to packet gaps in the multicast stream that we have encountered in our TAC interactions. And for everyone's reference, we have prepared a lab topology diagram, and we already sent it out to our registered customers last week. But we'll also be highlighting this topology in between the debug scenarios. And it'll be a good idea to take a snapshot of this topology and keep it up on your screen for reference. We have a PDF download link available in the Q&A section, which our panelists are putting now. So I definitely recommend everyone to download it and keep it handy during the course of this presentation. Along with Upasna, we also have our technical leads as part of the panel who can help answer any question that you may have during the presentation. You can use the Q&A manager to ask our panelist any question at any point of time during the course of this presentation. And before we dive into the troubleshooting scenarios, I would like to highlight, Upasna, can we move on to the next slide, please? Thank you. I would like to highlight that we are now also offering fully customized training sessions led by our TAC experts in our custom training product line. We customize the content of these sessions based on the feature set, platform, and the designs that our customers have in their specific network environment. We also include a comprehensive analysis of the recent TAC cases as part of these sessions to provide you a complete 360 view of your network and the problems that you've been experiencing in your network, along with key recommendation from our experts to overcome these problems and avoid outages. These sessions are delivered in the form of debugging sessions to ensure the readiness of your network operations team to handle any such challenges. And since we started this offering, we have delivered many such sessions to our customers, and we continue to receive great feedback on quality as well as on the content. This is a paid offering, so if you are interested in scoping a session with us or just interested in learning more about this offering, please reach out to us as tac-custom-training@arista.com. And without taking any further time, I'll hand it off to Upasna for taking you through the presentation. Upasna, take it away.
Thanks, Lokesh. Hello, everyone, and thank you for joining us today for our debug session. Just a quick introduction. My name is Upasna, and I've been with Arista TAC for almost 10 years now. And as Lokesh mentioned, today we're going to talk about a personal favorite topic of mine, which is multicast. The theme of our session today, as you can see, or rather not see, is to tackle gaps in multicast streams. And whenever we think about gaps, it's usually considered the bane of multicast troubleshooting. And while it's not this bane, it's, just as challenging. And the reason it gets such a bad rep, it's because, oftentimes gaps are not deterministic. And in many of those instances, when we see gaps, they're not actively ongoing when you sit down to debug, or if you've called in the TAC team for assistance. So in this session, we are going to tackle these gaps in two parts. First, we want to try and narrow down where we start debugging by asking more questions about the nature of the failure itself. And second, once we've narrowed down the scope, we want to go through whatever tools we have within EOS that can be leveraged with the help to help us, with historical debugging. All right. Before we begin, I do want to run a quick recap on some of the acronyms that I'm going to use today. And you might already know them, but let's just go through them anyways. So first up, we have our RP, which is the rendezvous point. It acts as the root of the L3PIM sparse mode design. This device is expected to always be aware if there are any sources or receivers in the network. Next, we have our DR, that's the designated PIM-capable router on a LAN segment, responsible for registering local receivers or sources to an RP. It's elected based on the highest configured DR priority, or if that's going to be the same, then the highest IP in the LAN. Now, depending on whether the DR is connected to the source or the receiver segment, it's either going to be dubbed as the first hop router, which is closest to the source, or the last hop router, which is closest to the receiver. Moving on, a GQ, which is basically a general query, is sent out by an IGMP querier in its broadcast domain. It's periodically sent in that domain to solicit reports from receivers who are interested in getting multicast traffic for any group. And this query is usually sent to the general all host IP to 24001. Now, conversely, a GSQ, or a group-specific query, is sent out by a querier after it learns that a receiver in a VLAN has indicated an intent to leave a group. The GSQ is going to be sent by the querier to ensure that, there are still other receivers interested in the same group. And the destination for that packet is going to be the IP of that group itself. All right, so with that, let's get a little familiar with today's topology. We have two sites. We have the red site and the blue site, and they're connected through their spine switches. Now, we are using BGP as our routing protocol, and the IPs that we are using on all the links are referenced in the diagram for easy lookup. Now, red spine 1 is going to be acting as a single RP for both the sites, and this is just for simplicity. We also have our applications that are going to be connected into the leaf layer, and these applications can either serve as sources, publishing traffic, or receivers, consuming data. All right, so let's take a look at our first problem scenario. We are receiving reports that our server team is observing that receivers in VLAN 200 are observing periodic gaps in their multicast stream. Now, the server team is unsure of when the problem itself started because earlier these receivers were not really equipped to monitor for gaps. But once they actually turned this on, they started to see regular reports of the problem. Now, our gaps don't actually have any specific pattern. They're seen randomly throughout the day, which means that, at least at this moment, they don't, for me, align to any specific event like market open or close or any defined multicast timer. When the gaps are seen, we see them for about 1-2 minutes at varying intervals, and typically they are resolving on their own. Now, as a sample, the last time we saw the gap was about an hour and a half ago from the switch time, around 5:07 to 5:09 p.m. Now, right off the bat, since the problem is periodic gaps, we can rule out typical issues that are listed in the slide that usually translate to traffic blackholing, and we've actually already covered a lot of these scenarios in our previous multicast webinars. That being said, we still have a pretty big scope because the issue could be at the source side, network side, or even the receivers. And I have listed some causes here that are top of the mind for issues related to gaps. But at this point, I don't have anything that I can really commit to, right? So step one, I need to build a better picture for myself. And I'm going to do that by starting to ask some questions, which can help me decide where I'm going to start my debugging process. And the questions can be different based on each symptom you see or the problem that you're seeing. But today we're going to use our scenario to get a general idea of, what we in TAC typically look for. So to start with, we want to know, let's say, if multiple groups are impacted. And in this case, our server teams confirmed that the problem is only seen for one group, which is 239.111, and it is being published to you by one source, which is 10.100.0.1. So at this point, our source is still in the race as a suspect. So our next question is, for this sample group, are there any receivers, let's say, outside of VLAN 200 that are also seeing the issue, all right? And for this, we learned that our receivers in other VLANs connected to other leaf switches are not reporting this problem. So an example would be receiver 4 and receiver 5. So with this, we actually have ruled out our source as a contributor. So moving on, we want to know that when our receivers in VLAN 200 are impacted, is that impact the same or is just happening randomly for each receiver, right? And here our application teams confirmed that whenever our receivers see an impact, they all see that impact at the same time. So now we could have an issue with delivery from somewhere from the source side of the network to the receiver side, or also, of course, the receivers themselves, right? So to eliminate a few more aspects of this network, my last question is, we have like a bunch of receivers in VLAN 200, but do we at least know one receiver, or like, are there all the receivers in that network seeing the problem at the same time, right? So here's where things get interesting. Our server team actually confirms that only a few receivers, namely receiver 1 and 3 in the diagram, are impacted, and receiver 2 has been fine. So with this, we've basically eliminated all of the device above the last hop router. And so our suspect is going to be somewhere at the last hop router or the receivers. All right, so with this, I think I'm reliably sure that I want to start troubleshooting, from the receiver side of the network. So we can jump onto the CLI and take a look there. And just a side note, while we reached our troubleshooting start just based on elimination, in general, whenever you're in doubt and, you don't have much to go on, it's always a good idea to start at the receiver side and then go and work your way up till the source. So to save us some time, I have pre-recorded the CLI portion of this, but I'm going to walk you through what my process was at that time. All right. So now we're on Blueleaf 1, and the reason we are here is because we suspected the problem to be either with the last hop router or the receivers in VLAN 200. And since Blueleaf 1 is the only PIM router on this VLAN, we expect it to be the PIMDR or the last hop router for this segment. We can confirm this by running show IP PIM interface. So let's run that. And here we can see for VLAN 200, the IP that's configured on Blueleaf 1 is the same IP that's elected as DR. Now, even in the steady state, which is what we have right now, and if the issue is not happening, I do always still like to start by looking at the mRoute on any device, because it's always a good way for us to get a snapshot of how that particular device is expected to be forwarding multicast data. So as a small segue, we're going to do show IP mRoute, and we're going to look at 239.111. And here we can see that we have our star G that's present for our group, pointing towards the RP, which was 192.168.11.1, with the receiver VLAN 200 correctly in our outgoing list. This same VLAN also got inherited as part of our SGM route for the source that we are troubleshooting, which is 10.100.0.1. The SP flag that you see on this mRoute indicates that the route is programmed in hardware, and we are forwarding on the source tree. This means that the incoming interface you see here, 53/1, that is the next hop interface for the best route that we picked from the unicast route table towards the source subnet, which is also, the route is reflected here in this output. Now, another value of note for this mroute is actually its uptime. Now, especially in cases with gaps, we typically want to see if this value got reset, because then that can help us justify the loss that we see. But that's not the case here, because the mroutes for the SGN strategy have been active for days, and the issue was only seen like an hour and a half ago. And this sort of makes sense because, during the issue time, receiver 2 did not report any gaps, and receiver 2 would have used the same mroute to receive traffic as that of receivers 1 and 3. So it meant that, we probably didn't expect this mroute to have a reset, which is what we have validated right now. All right, so let's shift our focus from layer 3 to the receivers themselves and take a look at the IGMP table. Our IGMP table is basically just an L2 table that represents what the IGMP snooping agent's oversight is for all the receivers in all VLANs connected to our switch, in our case, BlueLeaf 1. So let's run the output to take a look at this table. So IP IGMP snooping groups, our group IP, and then detail. Now you'll notice that this output also has an uptime. And the uptime here represents the uptime of when an IGMP report for the specific group, and in our case, that's going to be 239.111, was first heard. And it looks like this uptime was also present for a while, like almost 6 days now. But that being said, I still cannot rule out if my receivers are flapping, because this uptime represents the first report that was seen and not the last. And this first report could have come from any of my receivers that are part of the member list here. So what we really need is a more itemized form of data. So for that, we can actually use a different command. It's show IP IGMP snooping groups, but local, and for the group that we want. And this is going to give us the individual information for receivers that we need. It already looks like, we're on the right track, because if you look at this output for receiver 1, 10.200.0.1, and receiver 3.3, both of these guys have more recent uptimes, an hour and a half ago. And that matches the time frame of when we last saw the problem. And in contrast to that, if we scroll down, receiver 2's uptime has been solid at about 6 days, which further confirms the observation by the server team that only receiver 1 and receiver 3 are complaining. Now, usually if this uptime gets reset in the snooping table, I think that, this means that either the receiver left or at some point it got timed out and then later rejoined our group. But that being said, our server team is relatively sure that once an application joins, it is not expected to leave throughout trading hours. So before we draw any conclusions and start blaming our receivers, we are going to need some proof that these receivers are actually flapping. And as a start, in cases like this, it would be good for us to see some history of the joins and leaves that are being received on BlueLeaf 1 from all of its receivers. And we do have a way to do that on Arista devices by using the event monitor feature. This feature is very useful when trying to do a look back on changing states in various tables like the multicast table, MAC address table, or routing tables, etc. And you don't have to worry if you did not have this configured at the time of the issue. You do have the option of going back and configuring it after the fact. So for us, I'm going to add this feature in now, and the syntax for that is event monitor. So let's go ahead and add that, and then we're going to focus on the IGMP table for changes. So for that, let's do show event monitor, IGMP snooping, and we'll run the whole thing. Okay. Now, we can see that during the time of our issue, receiver 1, that's connected to Ethernet 5, receiver 3, connected to Ethernet 21, were removed for the multicast MAC that's associated with 239.111. They do get added back at a later time on this device. But if you look at that leave join window in the timestamps, it's 507 and 509. And this matches perfectly with the last window of gaps that got reported to us. Now, before we move on from this output, there is still one more interesting data point here, and that is preceding the events of receiver 1 and receiver 3. Now, just before these guys are deleted, we're actually seeing a short-lived join and a leave from a completely unrelated interface, Ethernet 3, for the same group MAC address, right? So if we scroll up more in this output, we can see that each time there is a leave from 1 and receiver 3, it always gets preceded by Ethernet 3 sending us a join and a leave. And we did discuss this with our server team, and they confirmed that Ethernet 3 does not seem to be connected to any known application, and it could in fact be a rogue device. But that being said, it's still odd for us because we need to understand how this random join and leave on a rogue device for our affected group is affecting stable receivers like 1 and 3. So for this, we are now going to have to shift our focus on the IGMP control packets themselves as received on VLAN 200 to check if you're actually receiving a leave from receiver 1 and 3, or something else is going on here. So if I want, I can run a packet capture on BlueLeaf 1 on VLAN 200, which is our receiver VLAN for IGMP. And this will be non-impacting because I'm only capturing traffic that's already on its way to the CPU. I could keep running this, but remember the issue is intermittent. And I can't actively run this TCP dump and wait for the next gap because I don't know when that event is going to be. It could be in the next 5 minutes, it could be in an hour, or it could even be tomorrow. So for this, we do have a feature in EOS, which we use pretty extensively in the TAC to help capture these one-off type of events. This is basically the TCP dump session feature, where we can set up a rolling packet capture that gets log rotated on Arista switches. So this way, when the issue is seen next, we were prepared, we already had something running in the background, and once the issues hit, we can remove that command in the session and pull the packet captures that got generated. Again, saving us some time, I have already configured one for us, so we can take a look at it right now. Show run section TCP dump. And the syntax for this is pretty straightforward. You can just configure TCP dump session, give it an arbitrary name, and then specify the interface you want to troubleshoot, just 200 for us. You can give a location of where you want to save it. So I'm sending it to Flash with the file name here. You can also provide a file count of how many mini files you want to generate for a session. I picked 5. But the main thing here is setting a max file size. This is so that we log rotate, and that way we don't take up space in the file system for something running in the background. Now I've capped mine to 50 MB, and you can do whatever works for you. And also maybe add a filter, in our case IGMP, because that's what we need here. We can do shows TCP dump, and that gives us an idea of how many sessions you already have configured on your device, and if any of them are active. So to move this along for us, I have already captured a snippet of the packet capture from the next instance where I hit the problem. So we're going to move to the capture itself and start analyzing the events during the gap window. So let's move over here. Taking a look at this packet capture, the time frame of our new instance is between 1:58 and 1:59 p.m., as I've highlighted here. And it's like about a minute of gaps. And the packet numbers that translate to this is 457 to 4784. And these are the only packets that we're going to focus on for this particular packet capture. Now, as a trigger, we see that even in this time, we saw a quick succession of a join and a leave that was received from 10.200, 0.100, which was that IP of the rogue application connected to Ethernet 3 on BlueLeaf 1. Now, the leave from this rogue device triggered BlueLeaf1, which is our querier, to send a group-specific query or a GSQ, which is highlighted here. The group-specific query basically said, hey, I saw a receiver on this LAN. It's no longer interested, but if there are any other devices that want traffic, I need you to send me an IGMP report within the max response time that I'm placing in my query, so I know you're still alive and want traffic. Now, we attempt 2 such queries each time we see a leave. So you can see that in the packet capture one's already highlighted. This is the next one. And by default, the max response time that we use is 1 second, which is also highlighted here at the bottom. So with 2 queries that go out with a max response of 1 second, we have about 2 seconds, after which we declare any receiver that doesn't respond back as stale. So in this packet capture, we can only see 10-200-02, which is receiver 2, responding back to both of our GSQs. And that explains why that's the only receiver that's not seeing the problem. But at this time, both receiver 1 and receiver 3 would have been deleted from the snooping table on BlueLeaf1 because there was no response from them. Now, at a later time, our querier, 10-200-0254, which is BlueLeaf1, will send its periodic general query, which we send about every 125 seconds by default. It's basically a request to any receiver in the VLAN to send a report for any group that they are interested in. And at this time, all of our 3 receivers, receivers 1, 2, and 3, are replying back with the report, as you can see just below the general query in the PCAP. So when they send their report, BlueLeaf1 can now go ahead and add them back into its snooping table. So any traffic that's routed in VLAN 200 can go to all 3 receivers. So everyone would have started to see traffic. Now, looks like what's happening here is that while we do have this, unintended device in the network sending leaves for 239.111, the main issue is that receiver 1 and receiver 3 applications do not seem to be configured correctly to respond to a group-specific query, causing them to get timed out till they send a more periodic IGMP report to the general query. So now that we have understood this issue, let's do a quick summary of what we saw, and then we can also discuss what are some potential ways to resolve this both in the short term and in the long term. So coming back to our slides. To sum up, our issue was we saw gaps in VLAN 200. And then, based on the initial questions we asked, we narrowed down our scope to BlueLeaf1 and the receivers that were connected to it. Once we started looking at the snooping table and event monitor tables in BlueLeaf1, we were able to confirm that during the issue state, affected receivers, receiver 1 and 3, were indeed getting reset inside the snooping table. We also saw evidence that there was probably a rogue receiver that was joining and leaving at the exact time frame that the gaps were being seen, causing us to suspect that that could have been a potential trigger to the problem. Now, when we configured the TCP dump, it helped us confirm this because every time we saw our rogue receiver join and leave was the key here. We saw that our querier started to initiate a group-specific query, which is expected. But then once this was sent, only receiver 2 responded. Receiver 1 and 3 were silent. And so they got timed out in the snooping table because the querier considered them stale. Now, in order to resolve issues like this, well, the long term, the answer is simple. We need to make our applications more robust and make sure that they understand the group-specific query and they respond within the time frame that's specified in the query. 1, they have to respond, and 2, they have to always respond within that max response time that's set. Now, we know that it's not always immediately possible to update the application, so we also need some short-term solutions. The first one, of course, could be just, shut down this rogue receiver, but that's not going to protect us from legit receivers rebooting or sending us a leave in the network, right? So till we wait around for the applications to get fixed, we can just adjust our max response time in the group specific query, which was 1 second by default, which we saw earlier. And we can align this instead to the timer of the general query. So this way our receivers won't time out, because we know that at least they're going to respond to the general query in about 125 seconds. And that way they can get considered in time for the group specific query as well. This command is going to be VLAN specific. So I've added this under SVI 200 for us. All right, so that's issue 1. Let's move on to our second and last scenario for the day. Okay, so it looks like on June 17th, switch time, between 9:44 p.m. to 9:48 p.m., which is about 2 hours ago from the switch perspective, our server team again, saw a gap in multicast traffic for multiple groups and multiple receivers. And this issue only happened once, but our server team is still concerned because they need to understand what this problem is so they can protect themselves from hitting something like this in the future. So just like last time, we're going to need a little bit more information before we get into the meat of this. As a start, we already know that the problem happened between 9:44 to 9:48, so that's a good start. But since many receivers and servers have seen the issue in this cycle, we do need a sample S, G and a receiver that we can follow for a more tangible approach. So in this case, we do have a source that's highlighted for us, 10.100.0.1, which publishes to a group 239.112. And this is one of the SGs that got impacted. The source, as you can see from our diagram, connects to red leaf 1. Now, a couple of receivers that the server team was able to identify as impacted that we can use for reference right now is 10.200.0.1, which is receiver 1 connected to blue leaf 1. We also have 10.201.0.4, which is receiver 4 connected to blue leaf 2. At the same time, our server team was also able to find one receiver, receiver 5, that's connected to red leaf 2, that did not see that gap during this window. So, unlike last time, we actually know that this time the problem doesn't seem to be isolated to just one leaf device, right? We have multiple and maybe more, we just don't know yet, right? So in this issue, we don't really have much more to go on than what I just said, because our server team is still assessing the full range of their impact. So we can't yet make any hard conclusions that, is the impact isolated to just one site, or is it, across the board, and we just don't know yet, right? But the only thing the server team can tell us is that whatever impact and whatever alarms they got during the time frame of the issue, it was for the same time across multiple S, Gs. So this becomes a little bit of a tricky problem for us because it doesn't leave us much space to figure out where we want to start troubleshooting. But we know that affected receivers were impacted at the same time. So likely the underlying cause we're going to find here in maybe one space is also going to apply to other receivers that got impacted. So before we actually start to debug, let's first figure out, since we don't have much more to go on, how this source connects to the receivers that we want to troubleshoot. Now, from the two receivers that got impacted, I'm just going to pick one and start tracing the path towards the source, because the root cause is going to likely apply to the other as well. So I'm going to start with receiver 1 that connects to blue leaf 1, and we'll jump into the CLI. Same drill. I have recorded this previously, and I'm just going to walk you through the process. All right, so we're back on blue leaf 1. It's connected to receiver 1 in VLAN 200. And on this guy, let's go ahead and run show IP route for the new group, 239.112. And similar to last time's S, G, we see that this time also we are using 53/1 for both the star G and for the S, G, which is towards the source, and our source is 10.100.0.1 again. Now from the LLDP neighbor or the diagram on the right, we can confirm that Ethernet 53/1 connects to its upstream spine, which is blue spine 1. And it looks like blue spine 1 is actually sending us a default route for both the source and RP subnets coming through Ethernet 53/1. And again, like last time, if we focus on our uptime here, it looks like both the SG and the star comma G have been around for a while again, for almost a day. So definitely not being reset at the time of our issue. Similar to last time, we also want to check our receiver side. So we'll quickly look at snooping groups local directly. And it looks like here are receivers. Receiver 1 has been stable for 17 hours now, including even the other receivers present on this device. So to continue to unravel the path of the packet, let's go on to blue spine 1. And on here, we're going to run show IPM route again. So let's do 239.112. And it looks like the incoming interface that we pick here for the source is 49/1, which again, reference it from the diagram and also from our LLDP neighbor, connects to red spine 1. Quick check again on the mRoute longevity here. It seems this has also been active for about a day, so definitely not in our 2-hour window. So going back one step up again to red spine 1, we're going to complete the path of our packet and run show IP route one more time. So 239.112. And here we can confirm our source interface is Ethernet 9/1. We are the RP, and looking at the LLDP, Ethernet 9/1 connects to our first hop router, Redleaf 1. Redleaf 1 is basically the starting point for the source in this network. So that's where our path of the packet ends. Now, the OIL 13/1 here connects to blue spine 1, which is sending us the PIM join for its receivers. We also see Ethernet 1 in 11/1, rather, in our OIL. And this connects to Redleaf 2. Redleaf 2 is where receiver 5 is connected. And just a reminder, receiver 5 was not observing any issues. All right. So now that we know the physical topology all the way to the source, we are still going to need a place to start debugging. At this point, we know that the issue is somewhere in the network. We don't really suspect receiver sides because, two receivers on two different last drop routers observing the impact at the same time makes it less likely to be an application issue. And the fact that receiver 5 did not report a gap, again, we've sort of ruled out the source from that data point also. Now, in my topology, debugging is a little bit easier because I only have 8 devices, but I do want to spend some time to build context that in an actual production environment, you could actually have a fairly complex path between the source and the receivers, and manually running these sanity checks on all devices in the path is not going to be an easy task. So this is why it's pretty common in multicast environments to incorporate spanning traffic or running a physical tap across key handoff points in the network, and then send it off to some kind of an aggregator. That aggregator can then forward this traffic to a remote collector, which can be any device that renders us historical data. And this is pretty cool for us in TAC because now if there's an issue, we have the ability to go back and look at historic captures and reliably narrow down where we want to start troubleshooting and also confirm the observations that are being seen. So if this is something that you don't have in your infrastructure right now, it's definitely something to think about. So let's go ahead and see what I have in my lab. I have tried to incorporate something with my smaller topology where I'm spanning all of my spine devices, because this is going to help me to understand, if it's my red site or my blue site that's originating the problem, or if it's my intersite link that is actually impacted between the spines. Now, taking a look at my design, I do have all of my spines sending traffic that is received by them to a remote collector. And each span session on the collector is tagged by a VLAN, so I can easily identify the flows from each of my spine devices. For example, red spine 1's flows will have a tag of VLAN 2116, and blue spine 1 flows will be tagged with 2114. Now, in my lab, I did use the Arista DMF solution where I sent traffic to our DMF fabric, which acts as an aggregator, and then it sends our flows to our collector, which is the DMF recorder node, from where I'm going to pull the packet captures later. That being said, honestly, you can use any device here that you have already deployed, and if it gets you the same results. So let's go on to my DMF GUI so we can go ahead and capture our packets. So for this, first up, we're going to have to jump into our collector, which is the recorder node, and then pull a combined capture from this from traffic received by both spines red, spine 1 and blue spine 1 in our issue window, which was 944 to 948 on June 17th. So once I'm going to query this out, I'm going to get a PCAP, kind of looks like a URL, which we'll download now and open and investigate together. Now, before we actually look at this PCAP, let's first figure out how to interpret this file. In order for me to be able to see the gaps, I added some sequence IDs to the last 4 bytes of my data. So you should see the packets increment sequentially in this capture. And if you remember, since the captures is a combination of what red spine 1 was receiving from the source and what blue spine 1 was receiving from red spine 1, in the steady state in the capture, we are actually going to see 2 copies of every packet. Anything tagged with 2116 is what the red spine got from the source. And immediately below it, you'll see the same thing with 2114, which is what the red spine 1 routed towards blue spine 1. And you can actually confirm this in the steady state because we see 2 of everything. For example, we see 2 captures for sequence number 66, 2 of 67, 2 of 68, and this sort of continues all the way down till our issue window at 944. Here we can see at packet 897, we have stopped receiving any traffic on blue spine 1 because we can only see 1 copy here, which is VLAN 2116, and that is coming to red spine 1 from the source. And back at the capture, we see this trend continue all the way till 948 till packet 4305. It's only at this packet number at 948 where we've started to see 2 copies again, which basically signifies that blue spine 1 has finally started to receive traffic again from our red spine connected to it. So this is very much our issue time frame, but it is important for us to note that throughout all this time, our receiver 5 does get traffic. So we can conclude that red spine 1 was able to route to red leaf 2 on Ethernet 11/1. But with the help of the captures, we have successfully confirmed that the same red spine 1 is not sending anything on Ethernet 13/1 that connects to blue spine 1. So what can be the cause here, right? To understand that more, we're going to have to go back to our CLI and start in reverse this time from red spine 1. And this is basically to determine why it's not sending the same multicast traffic on one of its outgoing interfaces, 13/1, that is able to send on 11/1. So coming back to red spine 1, to save us some time, I've already ruled out things like congestion, layer 1 issues, and other things. And I also don't think that we are routing in software right now on red spine 1, because if that was the case, receiver 5 would have also been impacted. So let's go back to that mroute we had run earlier for 239.112. Usually there is like a possibility that the reason red spine 1's not sending on 13/1 is because maybe it just got deleted from the outgoing interface list. And to see if something like that could have happened, we can rely on our event monitor feature from last time, but this time focusing on the L3 mroute table. So let's look at this for group 239.112. And then we'll grep for our issue time frame, which is around 9 o'clock. And here we can see that 13/1 going to blue spine 1 was removed at 9:44. And then it did get re-added back in the same output at 9:48, which again matches the delta of the loss that we saw in the earlier captures. Now, in a normal scenario, not seeing this Ethernet interface being removed, it could be because blue spine 1 did not send us a join, and as a result, red spine 1 timed it out, or blue spine 1 explicitly sent us a leave because it no longer had receivers of its own downstream. To understand this better, we're going to again go back one hop to see first what happened on blue spine 1, and then we can figure out what happened to the rest of the network. So on blue spine 1, same drill. We're going to run show event monitor mroute again to see what happened here, since the receivers are not local. And then grep for our group .2 and then 9 o'clock. And sure enough, we do see that we deleted Ethernet 49/1 that connects to red spine 1. But this is also odd because there does not seem to be any reason for us to do that, because we don't actually see a corresponding leave coming from any of the downstream interfaces that connect to the receivers behind blue leaf 1. That being said, that next message here shows us a null incoming interface for the same mroute, which usually indicates that we don't have a route to the source. But in our steady state right now, if you look up the route to the source for 10.100.0.1, we do have a route. And this goes through Ethernet 49/1, which on the diagram on the right connects to red spine 1. Now, if you look at the BGP neighborship between the spines, we can see that the neighborship has been established and stable for the last 7 days. But we do know that, while BGP is stable, our routes within BGP don't really have to be. So for one more time, we're going to peek into the event monitor table. And this time we're going to do this for the unicast routing table, just to see if there were any flaps for the source subnet. So show event monitor route. This time we are going to grep for the source subnet 10.100.0.0. Again, grep for 9 o'clock though. And here it does look like the route for 10.100.0.0 was removed for some reason. But we know that we can infer that red spine 1 upstream to blue spine 1 would have still had this route to the source because it was still able to service traffic to receiver 5. This means that the route itself could not have been withdrawn by red leaf 1. That's the device that actually owns this subnet. So what can cause blue spine here to unlearn this route? All right, so for this, I'm going to try to skim through our syslogs first to see if there was any network event. So last 2 days should be good. We'll grep for 9 o'clock. And the idea here is to see if there's something in our syslogs that justify what we saw around 9 o'clock. So, all right, so it does look like there was something around this time. It looks like at 9:44, we did make a configuration change to blue spine 1, which is definitely a red flag, because what if what was configured interfered with our network? So to take a look at what was configured at 9:44, we can either ask the network team, or we can also just directly use the EOS features to dig into historic accounting data that's already maintained on the devices. So I'm going to opt for that. We're going to do show AAA accounting logs, which is our way to see historic commands that are run on the switch. We'll grep for June 17th. That's when the issue happened. And then go closer to time at 9 o'clock. Now, it looks like there was a bunch of stuff happening here around this time. And some of it might just be periodic monitoring through scripts. So we're going to ignore that. But if we scroll here, we can see that there was a route map that got added here by the user to the red and the blue spine neighborships. And perhaps it was just the user trying to curate networks that we install into the blue site from the routes that get advertised from the red side, and that's completely fine. But if we take a look at the prefix list that got used as part of this route map, so if we see here, I think the prefix list is red subnets. It seems that the user might have made a mistake here at sequence 50 and at sequence 60, where they only allowed aggregates and not the individual subnets. And this is actually going to be a problem because our red spines are not currently configured to aggregate their networks, which means that all those /24 source routes are not going to be permitted on the receive side. But it does look like the user also figured this out because 4 minutes later, the user has gone in and corrected the prefix list. So at this point in our network, we should be good, and the server team does not need to worry about a problem in the future. We just need to make sure we look at our change controls a little bit more closely. And at the same time, from us in TAC, we also have an explanation of what happened during the issue timeframe on Blue Spine 1. And likely this might have also happened on Blue Spine 2. So with that, we are going to stop the CLI part of our session and then go back into our slides to sum up what we did today. All right. So in summary, we saw just one instance of the gap that was reported on some receivers. We picked receiver 1 and 4 today. And at this time, we had no idea, what was the full impact, how many receivers were impacted, and receivers in how many sites were impacted. So as a start, because we were focusing on receiver 1, we took packet captures between red spine 1 and blue spine 1 to investigate at least which site was introducing the problem. And with the packet captures, we were able to see that red spine 1 was not putting any packets on the wire on Ethernet 13/1 towards blue spine 1. When we tried to use event monitor mroute, we confirmed that the reason that red spine 1 was not sending the packets was because blue spine 1 had gotten removed from its outgoing interface list. And when we looked at blue spine 1, it looked like it had just stopped sending the joins. And this was very odd for us because, there were no receivers at that time. No one had left, which we had also confirmed from blue leaf 1. We saw evidence of the route being timed out towards the source. And we confirmed that by looking at show event monitor route. And that helped us confirm that blue spine 1 had stopped sending these joins because it had lost its route towards the source. Looking at historic accounting logs, we were able to confirm that the reason for us losing our route to the source was because there was a route map that got added on blue spine 1, whose prefix list essentially prevented us from accepting any of the source subnets into our routing table because it was aggregating versus us receiving individual /24s. Now, once this route map was corrected, which was about 4 minutes later, the multicast feed resumed. And this is something that we'd obviously also seen in the packet captures earlier between red spine 1 and blue spine 1. And just to save us some time, it was later confirmed by our network team that the same route map that got added on blue spine 1 was also added on blue spine 2. We could have also confirmed that through AAA logs on blue spine 2, which would have confirmed to us basically at a later time once all the impact assessment was done, that in fact it would be only the receivers in blue site 1, in the whole blue site, that were impacted for any of the sources that would have been coming in from the red site. All right, so that concludes scenario 2 for us today as well. I have summarized the commands that we used in both the scenarios here for quick reference. In the future, along with some additional reference articles that I personally find extremely useful to debug general multicast issues. And please definitely go and check these out in addition to the previous webinars we've had for multicast if you haven't already watched them. And so with that, we're almost done at the end of the session. I hope this session was useful, and I hope that the tools that we covered help you in your debugging for a varied range of symptoms in the network, whether that's multicast or pretty much any other protocol. especially when you're trying to debug any issue historically. So with that, I'm going to hand this back to Lokesh, who's going to help us conclude the webinar.
Thank you, Pasna, for providing such a detailed overview of this topic. The technical depth, what you have covered today is truly valuable, and we really hope sincerely that this session was beneficial to all our customers who joined us today. Again, the recording of this session will be available on our Arista community page, along with the presentation reference material and the questions that we covered as part of the webinar. But I would like to emphasize that along with these materials, there are several good articles that are available on our Arista community, which can be helpful for various other topics. So we definitely recommend everyone to leverage that knowledge base. And also, I would like to highlight that our fall series sessions are scheduled at this point. A quick update on the schedule. We are going to take a short break, summer break for the next 2 months, that is July and August, and we are going to resume in September with a more interesting topic focusing on AI network fabrics. So definitely looking forward to have you on those September sessions as well. And taking a cue from the technical deep dive that we just went through, if you're interested in scoping custom training sessions with us or just interested in learning more about the TAC custom training, please do reach out to us as tag-custom-training@arista.com. We have also put in a short feedback form link with 3 to 4 questions in the chat. So I request everyone to take some time to provide your feedback through that, as we definitely intend to use it for our future sessions. And at this point, I'm going to keep the webinar open to wrap up on the Q&As and answer any questions that you may have. You can use our Q&A manager to provide your feedback or ask our panelists any questions at this point. Cool. So if there are no other questions, then we are going to wrap it up. Thank you, everyone, for joining us today. Looking forward to see you at our next session in September. Take care, guys.
Thanks, everyone.